So this is the final lesson video for 8-3 day 2, the final example. It's example 3, and this time we're going to be revolving around the line we hadn't before. So they would like us to find the volume of a solid generated by revolving the region bound by the curves that they gave us, same curves, around the line x equals 4. So take a minute and on your graph, sketch the curves in that region that's bounded by them and the line x equals 4 and label everything. Then see if you can sketch the solid as it revolves around that line x equals 4, which will be unique in the sense that it's going to look a little bit different than the last two. If you're back, compare. I've got my region shaded. I've got everything labeled on my region. I've got which line it's rotating around. And a sketch of the solid reveals that when that rotates, it's going to be a solid in these portions. The top will be a circle, and then we'll have these parts, but there's going to be a hollow space in the middle. So this idea of slices of this will reveal that our slices cannot be circles. Our slices will have to be what we call a washer. And a washer means that instead of being circles stacked up, it's actually things with a hole removed, and at each level of my solid then, there's a circular part here and over here. We're not seeing all of the solid. I can't go 3D here. But there's a hole in the middle, so that each of those slices has a hole to represent how that kind of curved space in the middle is empty. So sketch your washer and see if you can figure out where the radius has to come from compared to that line x equals 4 that runs through it. To do that, it might help to come over to your picture and relabel a few things. You have your line x equals 4 in x equals form, and you have your other end x equals 0. So it's easy to tell that the full size big radius on this thing would go from this center line out to 0 and be 4 long, so our large radius. But our inner radius is a little harder to notice because our inner radius is going to need to be that circle that's missing to make this hole in here. So our inner radius is going to have to come from the distance between x equals 4 and this curve that at the moment is not expressed in x equals terms. So we need to move that curve around so that we can express the other radius in terms of the same variable. So if I go to my washer, my outside radius, we already decided, is that distance between any point on this line x equals 4 and any point on the line x equals 0 to get that outside set aside. So our big radius is 4 on that washer, that annulus. Our inside radius, we just rewrote this in terms of x's on the last slide, our inside radius goes from that center line out to this curve. So that center, or that smaller radius is going to be the quantity 4 minus y squared, so that we get the length of that smaller one. So area for our washer then is going to be the plan we've talked about all along. Area for that's going to be area of the outside circle minus area of the inside circle. So in our case, 4 squared pi will be 16 pi, pi r squared for the outer circle, minus pi r squared for our inner circle. With the area then, the integration is going to go the same way to get our volume. Forgot I didn't put the next slide in. So our volume is going to say I need to add up all of those washers. So the volume of our solid of revolution is going to be integrating, meaning adding together the areas times thickness, the volumes of each of those individual slices squared dy. And then I have to find my bounds. Well, if I'm in terms of y here, then I need to be sure that I'm in terms of y. Let me just fix that squaring so we don't have an extra parenthesis. But if I'm going to do a dy, then I need to make sure that my bounds are in terms of y. So my lowest y will represent the bottom ring, and my highest y will represent the top. So we're going from 0 to 2 as far as our y's go. So once we integrate, we should end up with a volume of about 46.914 cubic meters.